Hello, everybody. Hope everyone's having a good weekend and a happy Mother's Day. So this week's material, we're going to finish up with trig functions. We're going to talk about the applications of some trig functions, and more specifically, the application of sine and cosine. The nature of sine and cosine graphs is that they're periodic, right? They repeat over some period, and the pattern will continue to go forever and ever and ever. So there are a number of real life applications that we can actually take the sine and cosine graphs and apply them to. So now that we know what trig functions look like and how we can work with those functions, how can that be useful? Well, any real life situation that is periodic, we can model to the best of our ability by using a sinusoidal function. So for this course, I'll just pick two and we'll focus on those. We'll look at some Ferris wheel type questions and some tides types of questions. But just be aware that there's more than just that. So here's just a list of a couple of examples. So I said tides and Ferris wheels, but sunrise, temperature, swinging on a rope, right? For those of you that have taken physics, you might have seen things like spring motion or pendulums that can also be modeled by using trig functions, right? And again, the whole idea is that it is periodic, meaning that it is some pattern that repeats. So if you think about like a pendulum swinging, right, it just continues to go back and forth over a period of time. And if you were to look at the distance from like the center of the pendulum, it goes up and down, just like a sine and tan graph, right, or sine and cosine graphs. So in order to deal with these functions, what we need to do is we're no longer going to be dealing with an x-axis that's going to be degrees or radians. What we're going to have to do is we're going to have to take that x-axis and change it into some other units, whether that unit is distance or time or whatever the case may be. So for these questions, we're going to be talking about time. So with the tides questions, we're going to be talking about the height of the tides over a period of time. With the Ferris wheels, we're going to be talking about the height off the ground, usually over, again, a period of time. But what we're going to do for all of these questions is whenever we're trying to figure out what like our b value is supposed to be, we're going to consider radians and not degrees. So let's just take a look at an example of these questions. So here's the first one, these Ferris wheel type questions. So a Ferris wheel has a diameter of 10 meters and rotates once every 12 seconds. The bottom of the wheel is 0.5 meters above the ground. So one thing that I like to do when working with these questions is when we talked about graphing sine and cosine functions or going from the graph back to an equation, I talked about this pattern of high, middle, low. And what that means is if you think about this Ferris wheel, right, you can kind of pick out the heights of all three of those points. So if I were to take my circle drawing tool here and draw out my Ferris wheel, right? So what do I know about this Ferris wheel? Well, I know that the Ferris wheel has a diameter of 10 meters. So the height from the top of the Ferris wheel to the bottom of the Ferris wheel is 10 meters, right? And I also know that the Ferris wheel is 0.5 meters above the ground. So if I have my like legs holding my Ferris wheel in place, this height from the bottom of my Ferris wheel to the ground is 0.5 meters. Okay, so then when I'm considering that, if we think about this idea of the pattern of high, middle, low, then right away what I can do is I can pick up, well, what are those points? So when we're talking about my circular Ferris wheel here, the high point is this point at the top here, right? This would be my high point up here, and then my middle point would be at the center of my Ferris wheel, and then my low point would be at the bottom of my Ferris wheel. So with this idea of high, middle, low, so the value of high is how high is that point off the ground. So if my Ferris wheel has a diameter of 10 meters and it's also already 0.5 meters above the ground, then this high point, the highest point of my Ferris wheel, is going to be 10.5 meters. And then my middle point, so if the diameter is 10 meters, that means that the radius is 5. So that middle point is going to be 5.5 meters. And then finally, the low point is going to be 0.5 meters because that's at the bottom of my Ferris wheel. So what this question wants us to do is it wants us to first graph what the trip on this Ferris wheel is going to look like as a function of distance and time, or height and time. And then once we have the graph, we're going to find a function. And then once we have a function, we can then use that function to help make predictions about the height at certain time intervals. So let's start off with the graph. So what else do I know about this Ferris wheel? So in order to kind of look at the graph of these functions, yes, we need to know the heights, like the y values of my graph, but I also need to know, well, how long does it take to do a full revolution? So for this one, it tells us that the Ferris wheel is going to rotate once every 12 seconds. So what that means is that 12 seconds is our period, right? Because once it does one full revolution and gets back to where it started, it's going to repeat that pattern, and that is the definition of our period. So this period of the Ferris wheel is over every 12 seconds. So question A asks us to draw a graph that shows a person's height above the ground, starting at the lowest point for two full rotations. So instead of 12 seconds, we're going to graph this thing over a period of 24 seconds. So let's do that. So I'm going to make my graph. And where can I place my points here? Sort of matters. I don't really care about negative times or negative heights, right? Because we already know that our Ferris wheel is going to start above ground. I don't necessarily care about when it before the time that we're looking at. So we're going to start with 0, 0, kind of being that leftmost and bottommost point. And then the maximum height our Ferris wheel goes up to is 10.5. So if I went uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then maybe a little bit further, get up to 11. Those aren't really spaced out very well. Maybe I'll redo those so it's a little bit nicer. 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll get it 11, so we can get up to 10.5. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 10, and so on. And then along my x-axis, 2, 3, 4, 5, 6, 7, 8, right? So what I'm going to want to do on my x-axis is I'm going to want to pick a scale that's going to make sense in terms of this question. So knowing that my period is 12 seconds, and I know that it takes a quarter of the period to jump between each of these high, middle, low, middle, high kind of idea. So what I'm going to do is I'm going to use my period of 3. So 12 divided by 4 gives me a scale of 3. So 3, 6, 9, 12, 15, all the way up to 24 because it's asking for 2 full rotations or 2 full periods, right? Just fill this in here. So now let's throw these points in. So we're trying to graph this. So draw a graph, show a person's height above the ground starting at the lowest point. So we're going to start at that point 5. And then every 3 seconds, we're going to go from our low, middle, high, middle, low, and repeat that pattern until we get to 24 seconds. So here at 0.5 is where our first point is. And then 3 seconds later, we're up at 5.5. And then 3 seconds later, we're up at 10.5. And then 3 seconds later, we're back down at 5.5. And then back down to 0.5. And then the pattern is going to repeat a second time, up at 10.5, down to 5.5, and then finally down at 0.5. So now if I connect my points, I get a graph that looks something like this. Right, and then what we can see from after graphing this thing is that, yeah, it does follow a sinusoidal pattern. And if you weren't sure, if we think about it in terms of a table of values, right, so what we know is that the height of this person is going to go up and down as time progresses. So if my x-axis were time and my y-axis were height, we could talk about, well, how high are they at 0 seconds and how high are they going to be after 3 seconds and 6 seconds and 9 seconds and 12 seconds. And what we would find is that we would get to these points that we're looking at here, right? So 0 0.5, 5.5, 10.5, 5.5, 0 0.5, and so on. All right, so there's my graph. So there's my graph of time and height. Right, so now that I have my graph over 2 full rotations, let's find the equation that represents this graph, right? So let's figure out what the equation of this graph is going to be. So when it comes time to do these questions, notice that, or remember back to when we were going from a graph to an equation, we said, well, there's multiple answers. That you could have, it could be sine, it could be cosine. There's multiple instances where you could have that graph starting. It could start at this x value or this x value or some other x value. For these graphs where they're specifically saying, okay, well, we want to start at time is 0, we're going to go ahead and assume that that point at x equals 0, that is the starting point of my graph. So if that's the case, if x equals 0 is the starting point of my graph, then it tells me what type of graph this has to be. Because I'm starting at a low, that means I'm going to be using a cosine graph. It's going to have a negative a value, and it's going to be a cosine graph. So now let's pick out my a, b, h, and k, and then we'll be able to go from there. So, so my a value, what is my a value? When you're talking about these Ferris wheel questions, if you think about what is a is the amplitude. Well, the amplitude is the height from the highest point of your graph to the sinusoidal axis, or the middle of my graph. It's also the height from the lowest to the middle of my graph. But if I'm talking about a circle, a circular Ferris wheel, that means that the amplitude is just the radius. So if I think about my Ferris wheel here, my radius is 5, so my amplitude is 5, right? So my a value is going to be 5. My period for this graph to go from highest point to highest point, or lowest point to lowest point, or it says in the graph it takes 12 seconds for one full rotation, so my period is 12. So we got to think about, well, what does that mean in terms of b, right? So how do I get a period of 12? What's going to end up happening here is, because we want to work in radians, or we want to take our work out of radians and turn them into seconds, my b value is going to contain some number that contains pi, right? So again, so we know that period is equal to 2 pi over b. So if I rearrange that equation, I get b is equal to 2 pi over my period. So my b value here is going to be equal to 2 pi divided by 12, or pi over 6, right? So there's my b value. Okay. My h value, nicely enough, is 0, right? When I'm starting at x equals 0, or time of 0, that means I don't have a horizontal translation, so my h value is just going to be 0. Then finally, my k value, well, again, if we think back to what we were doing previously, the k value is your sinusoidal axis. It is that midway point of my graph. So what is that in this one? It is 5.5. Right? So from here, I'm just going to take my a, b, h, and k numbers and plug them into my equation. So y is equal to, so again, we're starting at the bottom of the graph, so that's kind of the upside down of the cosine. So negative 5 cosine of b, so pi over 6x plus 5.5. And that is the equation of my graph. And I'm not just like suggesting that you use this h, or this x value of 0 here. I'm really, really highly recommending it, because in question C, now that we have a function, it's asking us to predict how high the person is going to be after 6 seconds, 12 seconds, and 20 seconds. In order to do that, we need to have an equation that assumes we're starting at time 0, right? So if I want to just take 6 and plug it in for x, then that means my graph has to start at 0. If I picked another starting point, or some different h value for my graph, I couldn't use 6. I'd have to use 6 in relation to that new point. So let's say, for example, I was like, okay, well, I don't want to work with cosines. I'd rather work with sines. So I picked 3 as my starting point. What that means is, in order to solve that question, I can no longer plug 6 into my x value. So just be careful with that. So for this question, let's use this function here, and let's figure out, well, how high will this person be after 6, 12, and 20 seconds? So what we're going to do is we're going to take those 6, 12, and 20, and we're going to plug them into my function for x. So y is equal to negative 5 cosine of pi over 6 times 6 plus 5.5. All right, and then just solve. So if we simplify that, so negative 5 cosine of pi plus 5.5. So the cosine of pi is -1, right? So -1 times -5 is +5 plus 5.5, and they are at a height of 10.5 meters. So there is that. The other option when solving these questions is, well, think about how many periods is that. So for example, if I'm talking about 6 seconds and a full period is 12 seconds, so what that means is that my 6 seconds is half the period. So if that's the case, I don't necessarily have to do these calculations to solve that answer. What I can do is I can think, okay, where is the sine graph after half the period, or a cosine graph after half the period? And after half the period, it went from the bottom of my graph to the top. So what that means is now I can kind of use that strategy of saying, okay, well, how much of the period is this? So for question or for part C, for 12 seconds, we could do the same thing and say, okay, well, instead of plugging 12 in for x and then trying to solve, what I can do is say, okay, well, 12 is one full period. So if I'm talking about a negative cosine graph, it goes from the bottom back to the bottom because that's one full period. Now you can always check that by plugging it in and saying, okay, well, I know that y equals -5 cosine of pi over 6 times 12 plus 5.5, and then y is equal to -5 cosine of 2 pi plus 5.5, and the cosine of 2 pi is 1, so we get -5 times 1 is -5 plus 5.5, which means after 12 seconds, my Ferris wheel is back at the ground at 0.5 meters, right? Kind of like what we said would happen because it went one full period. So that's great if my x values are some kind of factor of the period. But if it's not a factor of the period or not a multiple of the period, like 20 seconds, then yeah, what we have to do is we have to take that 20 seconds and plug it into my equation for x. So we get y equals -5 cosine of pi over 6 times 20 plus 5.5, which is -5 cos 20 over 6 is 10 pi over 3. So 10 pi over 3 would be, so 10 pi over 3 plus 5.5. Now, you don't necessarily have to use 10 pi over 3 because if you think about it, your period, right, your graph is going to restart after your period. So going from 0 to 12 seconds is exactly the same thing as going from 12 seconds to 24 seconds, which is exactly the same thing as going from 24 to 36, and so on and so on and so on. So if that's the case, using 10 pi over 3 is kind of a big number, right? It's something that we don't really deal with that often because normally we only go from 0 to 2 pi, and this is 3 and a third pi. So it's a little odd, but what we can do is instead of considering 20 seconds, I know the same thing is going to happen after 8 seconds, right? Because of the repetitive nature of these Ferris wheel questions or these sine graphs or cosine graphs, right? So because my period is 12, that means 12 seconds prior to the 20 seconds, we're going to be at the same height. So I could just as easily have done this question. Instead of 20, I could have plugged in 8, and I'll get the same answer. So pi over 6 times 8 plus 5.5, which is -5 cosine 8 over 6 is now 4 pi over 3 plus 5.5, which is a little bit more what we're used to seeing, right? So 4 pi over 3, that is in my third quadrant after pi over 3 radians. So this cosine of 4 pi over 3 is going to be the same thing as the negative of the cosine of 1 pi over 3. And the cosine of 1 pi over 3 is 1 half. Think about that for a second. Yeah, so it's 1 half. And if you're not sure, what we can do is we can take our calculator, right? We can grab our calculator and we can plug it in, right? So we could say -5 times the cosine of actually, just give me a second here. Still in degrees. Got to change that to radians first. The cosine of 4 pi over 3 plus 5.5, and I get an answer of 8, right? Or if you are comfortable with using your special triangles and your casserole, right? So this is -5 times -1/2 plus 5.5. So we get 2.5 plus 5.5 is 8 meters, right? Okay, so let's take a look at another one of these questions, and maybe let's go through it a little bit quicker this time. And again, at any point in time, if you guys think you could want to try one of these, go ahead, pause the video, and then come back. So again, we have a Ferris wheel with a radius. This time it has a radius of 10 meters, and it rotates once every 60 seconds. So with this last time, we had a diameter of 10 meters, and what that meant is that our amplitude was going to be 5 meters because it's 5 meters above and below the center. So now what we have is we have a Ferris wheel that has a radius of 10 meters. So that radius, that is going to be my amplitude, and it rotates once every 60 seconds. So again, the amount of time it takes to go through one full rotation, well, that is the definition of your period. So right in the question, we have our amplitude and we have our period. So if passengers get on board 2 meters above the ground at the bottom of the Ferris wheel, so the bottom of my Ferris wheel is 2 meters above the ground. So what we want to do again is draw an equation and draw a graph and write an equation that's going to represent this Ferris wheel. Now, this question doesn't necessarily ask for a graph, but you might want a graph because it'd be a little bit easier to pick out these pieces of information by having that visual representation. So it might be worthwhile to draw a graph if you're not sure how to find the A, B, H, and K values. If you're pretty confident in your ability to find those, then that's fine. Just go for it and see how you can do. So again, here's my circular Ferris wheel with my center here. My radius is 10, so it means that the entire diameter from bottom to top of my Ferris wheel is going to be, put that over to maybe closer to the middle, is going to be 20 meters, right? And the height from the bottom of the Ferris wheel to the ground is another 2 meters, right? So then if I wanted to look at my high, middle, low points here, well, my high point is going to be this bottom part plus the 20, so 22 meters. My middle is going to be this bottom part plus the radius, which is 10, so 12 meters. And my low is the bottom of my graph, which is 2 meters, right? So if I wanted to draw this, maybe just over one period, I need to go all the way up to 22. So if I went 5, 10, 15, 20, so a little bit above that will be 22. And it takes 60 seconds to go one full rotation. So again, I'm going to want to scale. That's 1/4 of that so I can make sure I'm getting in that pattern we're looking at, right? So quarter of 60 would be 15, 30, 45, 60, 15, 30, 45, 60, and here 5, 10, 15, 20. All right, so now if I wanted to graph this, I know that I start at a low. So I start down here at 2, and then every quarter of my period, I jump up 10, and then I jump up here to 22, and then I'm back down to 12, and then I'm back down to 2. So my graph looks something like this right here. All right, where my sinusoidal axis is here at 12, right? My amplitude, we already said, is going to be 10. My period is 60. So now from here, what I can do is I can start finding my A, B, H, and K values. So again, my amplitude is 10, so that's going to be my A. My period is 60, so we're going to find B by taking 2 pi and dividing it by 60. So we get pi over 30. My H value, there isn't any, right? There is no horizontal translation because we are starting at 0. And my K value is going to be my equal to my sinusoidal axis, so up here at 12. So the equation that's going to describe this graph is y is equal to negative, right? Again, it's negative because we're talking about the inverse or the upside down cosine graph. So negative 10 cosine of pi over 30 x plus 12. All right, so then part B says if Emily is at the bottom of the Ferris wheel, when it begins to move, determine her height above the ground to the nearest tenth of a meter when the wheel is in motion for 2.3 minutes. So again, for these questions, you really have to pay attention to the units, right? So what I said at the previous, when we started this section, was that we're not going to be dealing with an x-axis that's described by radians or degrees. We're going to have an x-axis that potentially is described by time, and I guess it should have been more specific. Well, what unit of times? Are we talking about seconds? Or are we talking about minutes? And it matters, right? So when we were given our period, we were told that it takes 60 seconds. So if it only takes 60 seconds, then how many seconds are there in 2.3 minutes? Because we have to make sure that we are in um, the same units. So again, this is one of those questions where, okay, well, it's 2.3 minutes. Well, we know that a period takes 1. So we know that the period is it takes 1 minute. So 2.3 minutes later, well, the same thing's going to happen at 0 minutes, at 1 minute, at 2 minutes. So 2.3 minutes is going to act like 0.3 minutes because every on the minute, right, we're going to be back down at our low point at 2. So when we're going to solve a question like this, I don't necessarily have to consider the adding the 120 seconds. All we really need to consider is the zero point 0.3 minutes, right? Again, it has to do with the fact that the graph is going to repeat the pattern every time we hit the period, every time we hit a minute. So the same thing that happens at 2.3 minutes is going to happen at 0.3 minutes. So we're going to have the same height, so we might as well use the lower of the two numbers just to kind of save ourselves. But it really won't make much of a difference. The only thing that really matters here is we have to make sure that we are um, in the correct units, right? So nice quick calculation here. So 2.3 minutes. So if we take that and we multiply it by 60, is going to be 138 seconds, right? So we could take the 138 seconds and plug that into our equation and then solve for the height. We could also just as easily use 18 seconds and plug that in our equation and solve for height as well. Like I said, either way, you're going to get the same answer. So if we take our y equals negative 10 cosine of pi over 30 um, times, well, I'll use the 138 just so we see, plus 12, right? So that's going to be negative 10 cosine of, um, actually, you know what? I'm not going to use the 138 just to make the mental math a little bit easier here because we want to simplify this fraction as much as we can. So this is um 3 pi over 5 plus 12. So for this one, what we're going to have to do is we really will have to grab a calculator because there isn't a special triangle that's going to use pi over 5, right? So we're going to have to use our calculator and say negative 10 times the cosine of 3 pi divided by 5 plus 12. And then what we're going to do is we're going to have to kind of round our answer. Our answer won't exactly be exact because it's an irrational number, but it is approximately 15.1 meters off the ground. Now, again, if you really aren't convinced, you could always grab your calculator and instead of plugging the 18 in, plug in the 138 and check your calculations there, right? So if I did that, if I did 138 over 30 and I hit equals, I get exactly the same answer. I still get that 15.1 meters. Okay, so here's a third question. What I would suggest is giving this one a try. And if anyone on Wednesday wants to ask me a question about this one, we can do it then. But I'm going to leave this one for you guys to try while I leave a little bit of time to talk about these tides questions. So if you take a look at these tides questions, so here's an example of a question. So let's say, for example, I wanted to create a model that modeled this data. So let's say I was working with a team of researchers out of UMBSJ, and they were collecting information about the Bay of Fundy, and they wanted to measure the tides over periods of time. So here could be my information. So what I can do is if I take that information and I model it on a graph, right, we can find things like my amplitude, my vertical shift, and we see right away, oh yeah, this does look like some kind of sinusoidal graph. And again, what ends up happening, depending on how I'm starting, if I'm starting at low tide, starting at high tide, or starting at my kind of mean sea level, right? what I'm going to get is I'm going to get either a cosine or a sine graph, right? So things like my sinusoidal axis are there, my period's there, my period, my horizontal shift. Now, one thing I would like to point out is the period for a um, tide graph is always going to be the same, right? If you think about what tides do, generally they take 24 hours to kind of go in and out, or 12 hours to go in and out. So we got to think about that in terms of our period. Um, right? So, like if you look at this question right here, we have what looks to be high tide here at 4, and then we look to have another high tide here at 16, 12 hours later, right? So that's what tides do is they're going to go in and out, and it takes 12 hours to go from high tide to high tide, right? So with any of these tide questions, if it's kind of left ambiguous what the period is going to be, assume the period is 12 hours. Okay, so let's take a look at one of these questions and then we'll call it a day. So the difference between high tide and low tide is 20 meters in the Bay of Fundy. So it's not necessarily telling us what the height of the tide is going to be. All it's telling us is that the difference between them is 20 meters. So if we think about the kind of the shape of my sinusoidal axis, what that's telling me is that from the highest point of my graph to the lowest point of my graph, that height is 20 meters. And then what the question wants to do is to draw a graph of the height of the water above mean sea level for a 36-hour period. So what that's telling us is it's not saying the period of my graph is 36 hours. It's telling us the period of time that we're considering. So again, when we're talking about tides, it takes 12 hours to complete a full tide. So what this is asking us to graph is it's asking us to graph a tide or a 3 full periods of my tide. So again, we don't know necessarily how high the tides are, but what this wants us to do is it wants us to make a graph that is relative to the mean sea level or the halfway point between high and low tides. So if that's the case, what I'm going to do is I'm going to make my x-axis, my y equals 0, that is going to be on my mean sea level. And then what's going to happen is this graph is going to be 10 meters above mean sea level at high tide and 10 meters below mean sea level at low tide. So this is one of those rare examples where we have a application problem that actually does consider negative values. But again, so now what we want to do is we want to pick a scale that's going to make sense. So again, remember that the scale um, for a graph should be a quarter of the period, and then consider your h value, but we're not going to have an h value here. So it's going to be a quarter of 12, which is 3. So 3, 6, 9, 24, 36. So there's my 12, 1, 2, 3, 24, 1, 2, 3, 36. So what's going to happen is my graph, if it starts at high tide, starts at low tide, in this question, we kind of get to make that decision, right? It doesn't say, so draw a graph of height of the water above mean sea level for a 36-hour period, then find an equation to describe the graph. It's not telling us whether it starts at mean sea level, starts at high tide, starts at low tide. So it's up to us to decide what we want. So if we want a sine graph, we're going to start with the middle. If we want a positive cosine graph, we're going to start with the high. And if we want a negative cosine graph, we're going to start with the low, right? So it's really up to us to decide what kind of graph we want, and that's going to tell us where we start. So again, what's going to happen is if I want a sine graph, I'm going to go from middle, high, middle, low, middle, high, middle, low, and so on and so on. So we're going to start at the middle, and then a quarter of my period, I'm going to be up here at high, and then back down to middle, and then down to low, and then finally back up to middle, and um, there's my one full period, and then the pattern is going to reset. So again, middle, high, middle, low, middle, high, middle, low, middle. Right, so then there's my graph here. And excuse the the messiness, right? The tablet's not the greatest tool sometimes for drawing these, but at least it's better than the touchpad on my laptop. All right, so then there's what my graph will look like. So then from here, let's pick out our key pieces of information. So things like my amplitude, So we are told the amplitude is 10 meters, right? Again, since the distance from high to low tide is 20, half of that will be my amplitude. My period for a tide graph is always 12 hours. So if the period is 12 hours, to find my b value, we're going to take my 2 pi and divide it by 12. So my b value is pi over 6. My h, right, again, for these application problems, the easiest thing to do is to consider h to be 0, right? No horizontal translation means we're starting at time 0. And then finally, my k value for this question, because we're graphing it about the middle or about that mean sea level, my k value is also going to be 0. So now the equation of this graph is going to be y equals, it's the pattern that we would expect for sine, right? It does that pattern. It's not upside down, so it's going to be positive 10 sine pi over 6 x. Right, so now if I wanted to look at, well, what is the height after blank hours, right, then I would just plug that number in for x, and this equation would spit out a height. Okay, so there's a couple more of these example questions. I'm not going to go through them right now. If anyone has any questions and you want to come ask them during the live session, then I'm welcome to that. Otherwise, if you guys want to try these just for a bit more practice, then that's up to you. So here's another one here. Difference between high tide and low tide is 15 meters. So similar type of question, but now we're talking about 15 meters. Draw a graph of the height of the water above mean sea level for a 24-hour period. Then find the equations. The same type of question. This time we're talking about 2 full periods because it's 24 hours, but it's still the same idea where the difference between high and low tide is 15, so the amplitude is going to be half of that, and we could go from there. And then finally, here's another question where if we have high tide is 22 meters and low tide is 10, so now it's worded a little differently, but it's still providing us with the same information. It's instead of saying that the difference between them is blank, it's saying, well, here's the high, here's the low, so it'd be up to us to find the difference. So draw a graph of the tide cycle for a 48-hour period. The other thing about this question is it's not talking about in relation to the mean sea level because it's giving us a 10 and 22 meter. Now I'm not going to have a graph that has a k value of 0. I'm going to have a graph that has a k value that's right in between the 10 and the 22 because the 10 is my low and the 22 is my high. But again, 40-hour period means that we're looking for 4 full periods of my graph. All right, so that's it for today's video or this week's video. So again, similar, we're going to have a live session Wednesday and quiz on Friday, and then by the time Friday is over, we will be officially done with trigonometry. So looking forward to getting on to the next content next week, and I will see you guys